Good morning, everyone. Hopefully you're having a lovely day so far. I am not quite ready to get to 8.2. I want to go through a few more things with 8.1. And if you guys had an opportunity to go through some of those questions from last day, you let me know if you had any problems that you ran into. I assume you can hear me. You're saying good morning, but let's go with green checks anyways, just so we can make sure we're doing okay. So I left you guys with the first section in the learning guide, and there was a few slides that I didn't get through last day, so I'll go through those. But I don't think they had a huge impact on the questions in the learning guide, so you guys will probably be all right to get most of those done. Just one question, that's okay. And like I was saying, as we get further into the unit, it kind of works out that some of the things we covered at the beginning get looked at again and again and again. So again, we're just kind of building the foundation right now. And then once we've built that foundation, then we'll, be able to use all this stuff. Number 4, page 1 for sure, Taylor, I can get to that. Ava, fire away, and Abby, yes. Let's wait till the end of the block, Abby, just in case I don't get to finish it all. I don't want to get too lost, but I have a feeling we'll have some time today. All right, page 4, number 1. From the learning guide. Are we going to run into this problem where our learning guides are different pages? Because page 4 I have, Taylor, I don't see a number 1. Unless you mean the first question on page 4, which is number 6. Or if you're talking page 3, number 1, the velocity question. Page 1. Did I mix that up? Number 4, page 1. Completely my fault. Put the following items into the correct category. Okay, so we're talking about vectors and scalars. If it has a direction attached to it, then it's a vector. If it doesn't have a direction, it's a scalar. So 1 kilogram. Can you associate a direction with a mass? Do I usually say, I weigh 1 kilogram east? Not generally speaking. So that wouldn't make a lot of sense to give a direction to it. So we can put it in the scalars. So remember, vectors have a direction associated with them. 10 kilometers per hour. That doesn't have a direction associated with it. It's just 10 kilometers per hour. I don't know which direction I'm going. Am I going up, down, north, south, east, west, forward, backwards? So that's a scalar. This next one, we haven't really talked about the notation of cardinal directions. We'll get to it today. So perhaps a little bit unfair to throw that in there, but when you see something like this that has, it's not what I wanted, when you see square brackets with a letter in it, that's like a compass direction. So north, south, east, west. That's kind of the notation we use. So we'll always put compass directions in square brackets. So in this case, 20 meters per second to the north, that has a direction associated with it. So we know we're going north with that velocity. Velocity is a vector, distance is a scalar. And distance is one of these tricky ones. Distance is just how far you went and not, doesn't have any sort of direction associated with it. Does that give you a good start on that one? So generally speaking, if you see something like downstream, down, southwest, these all have directions associated with them. So as soon as you see a direction, you know you are a vector. There's a few exceptions in here, things like velocity and acceleration. Those are vectors. We always include a direction with those, but generally speaking, for the examples that are there, you should be all right with that. All right. Question number 13. Check your answer, says 500. You got 447.2. Number 5 in the learning guide. Page 1, yes, but wanted to see what you think of the question. Can 3 parallel vectors, unequal magnitude, add to 0? All right, that's a good question. So parallel means that obviously they're going in the same plane. So we could think about it in terms of up, down, forward, backwards, north, south, east, west. Doesn't really matter. So let's start with a vector. Let's draw it horizontal to there. All right, so there's a vector. I don't know what length it has. We'll call it 10. Unequal magnitude. That's not going to work. Let's call it, let's call it 5. That's better. And then I could have another vector going this way. We could call it 2. And I could have another vector going this way. I could call it 3. And do they add to 0? Yes. I'm back to where I started. My end and my beginning are at the same point. So, yeah. So that's how you could end up with a situation like that. And Ava, number 13. Let's scroll down to that fella. Whew. One thing about question 13, I'm happy you did it, Ava. In the notes, there's some information on vectors that are perpendicular to one another. That's the type of question we're dealing with here. Now, I looked at a bunch of old provincial exams. I looked at some of the example exams that are online. And it turns out that there's never really been a question with kind of 2 dimensions that I could see. There, generally speaking, won't be anything like that. It's kind of a grade 11 sort of topic in Physics 11, not a grade 10 topic. So I'm not going to spend too much time focusing on it, but I will happily do this question just to make sure we got it right and the answer is indeed wrong. Okay, let's draw our plane. Our plane is this dot. Like I said, always draw a picture, even if it is a dot and arrow type picture. So 400 kilometers north. There's 400 kilometers. Put that on the other side. And then we're flying 200 kilometers west. And what's the plane's total distance traveled and displacement? So the first thing it asks is distance. And remember, distance is just how far you went. So if you started here and you went up and over, well, you traveled 400 and then 200. So that's going to be 400 kilometers plus 200 kilometers is 600 kilometers. There you go. So your distance is going to be 600 kilometers. The second part of the question is the displacement. So displacement is how far are you from where you started? Now in this case, I'm going to have to draw in my resultant. And I'm going to use the Pythagorean theorem to solve that. So I'm going to go 200 squared plus 400 squared is, we'll call it r for resultant, r squared. I'll fire it into my calculator here. 200 squared plus 400 squared. And we're going to take the square root of the answer. So 447.2. There you go. So that is your displacement. So there you go. You guys were on the right track and you got it completely right and the answer is wrong. It's one of these things we don't know until we get to it. Number 12, fish swims 50 meters north, then 10 meters east, then 40 meters west. Sketch and solve. All right, so again, we're going to draw a picture. So 50 meters north, and then he's going to go 10 meters east. So this is 50, this is 10, and then 40 meters west. Sketch and solve. All right, so we're looking for the resultant, and we're going to draw this triangle here. So I'm going to redraw this triangle with a complete set of information. So I started there, and I went 50 meters north. Now, there's no other vectors in the north-south direction, so there you go. And then it said 40 meters to the west, but I've already gone 10 meters to the east, so this is only going to be 30. And then I want the resultant from there. So you guys are capable of solving that. Probably just setting it up was a bit tricky. And Abby, yes, I'd love to say that we would include incorrect answers to make sure you are thinking about what you're doing, but unfortunately that's not the case. It's just incorrect answers due to human error. I'm not really sure why there's so many incorrect answers, but there are. What are you going to do? Even textbooks have this problem. It's just kind of a reality of having humans do work and then they make mistakes. Or from time to time, they'll change the questions, add different numbers, and then forget to change the answers. So there's lots of ways that it can go wrong. All right, is there anything else from that portion of the learning guide? I'm just going to jump over to the 8.1, just to finish it up. I went through the majority of it last day, but there was a few things I didn't get to that I just wanted to run through real quick. So we did end up here, distance displacement, and we started talking about the difference between the two. Remember, distance is kind of like the odometer on a car. It just counts up. It doesn't care what direction you're going. It's just counting, moving, and you stop, and then it stops. That's what distance is. Displacement is your change in position. So if you started somewhere and you ended somewhere else, how far did you go from where you started to where you ended? That was your change in position, from where you started to where you ended. It's kind of the difference between those, and they sound really similar, so it can get really confusing. And even I have issues when I haven't seen the stuff for a while. I'll go back to it and I'll kind of look at it and be like, distance, displacement, what am I trying to find here? So just an example quickly of that is between 0 seconds and 15 seconds, the person's displacement. So it's kind of a weird picture where this guy is walking, but he's not walking at the same speed. He's kind of speeding up and slowing down. So you need to pay attention to the time stamps at the top here. So you have 0 seconds, and then I look for the next one. So 5 seconds, he's over here. So in the first 5 seconds, he went to this 20 meter mark, and then 10 seconds, he's here. And then 15 seconds, he's way over here. And then 20 seconds, he's back here again. Use my little laser pointer. Yeah. All right, so from 0 to 5 to 10 to 15 to 20. Kind of a weird scenario. Between 0 and 15 seconds, the person's displacement is. So if I was asking for distance, I'd have to add up that, plus that, plus that. But it's not asking that. It's asking the displacement. So the change in position from when I started to where I ended. And in this case, it's asking at 15 seconds, not at 20 seconds. So what is the displacement? What is the change in this person's position? The reason this is a little bit tricky is because in this example, you aren't starting at 0 meters. The person's actually starting 5 meters to the right of some random reference point here. So 0 seconds actually happens at 5 meters to the right, or in this case, east, 5 meters to the east. So we could answer it 2 ways, and Alex, you're right. So the person walked 5, 10, 15 meters to the west, or we could talk about signs. So we could give this a negative sign. So I think Abby had mentioned something last day, and I said, well, there's 2 right answers. We could say it's 15 meters to the west, or we could say it's negative 15 meters. They both mean the same thing. And that's what we're going to get into here. And for all of physics, this is very standard throughout everything you do in physics, whether we're talking about acceleration, speed, position, we always use these sign conventions. So 15 meters west is, that's right, well done. So these are the sign conventions for physics. And this is always the case unless it makes sense to do a problem without these. And that'll sometimes happen, but not till grade 11. So if you're dealing with anything to the west, to the left, we always give that a negative sign. Not always, but almost always. If we're dealing something to the east or right, we give that a positive. If we're talking about north up, we give it a positive. And if we're talking about something that's south or down, we give it a negative. So generally speaking, things to the right, positive, things to the left are negative, things up are positive, things down are negative. That's just kind of the convention we use. So now we can always have 2 answers to our questions that are vectors. We can have negative 15 meters. So as soon as I see negative, I know it's talking about the left or moving west. Or if I see negative, it could be talking about down or south. I just need to kind of understand the context of the question. So if the question's talking about something falling off a cliff, then I know I'm dealing in an up-down direction. It wouldn't make any sense for negative to mean left. So that's just kind of the stuff we run into. I don't think this is worth going over, so I'm not going to. There was some questions in the notes that had more than one dimension. So talking about going north, south, east, west, like number 13 we just looked at. It's really important to know that you won't see anything like that on the provincial. Now, I don't want to say you won't see it on the unit test or the unit quiz. It's likely that you will see it there, just because that's kind of the person who made this course included those 2-dimensional type questions. But it's pretty basic stuff that like Pythagorean theorem type questions, so you guys should be okay with it. If you do run into a problem with it, you can flag it and I'll look at it, and I'm pretty easygoing when it comes to that stuff. If it's not something you probably have to know, then if you don't get it, then we can talk about it for sure. On the provincial, I don't want to say that that it's always going to include a direction, but from what I remember, generally speaking, the provincial exam will always use a direction. So instead of just saying negative 15 meters, it'll say 15 meters to the west or 15 meters down. So yeah, generally speaking, the provincial will include a direction, but of course they don't have to, so I don't want to kind of guarantee that. So that was 8.1. I almost finished it, but I didn't. And then I went back and looked at it again, and I thought, well, this 2-dimensional stuff you're not going to see, so it's kind of unfair to ask a bunch of questions on it. So don't focus on the 2-dimensional type stuff. When I say 2-dimensional, I'm not talking about like forward, backwards. I'm talking about going up and then going to the left, or going up and then going to the right, or down and then, going east, or things like that. What I wanted to get to today was section 8.2, and we are going to just keep rolling. I think we might finish chapter 8 today. Just depends on how long it takes us to get through these questions. I'm always a bit optimistic when I look at the material, and then it usually takes me longer to get through it. So today we're going to talk about velocity, and Velocity is different than speed. So in physics, we'll talk about both speed and velocity. How does trigonometry have to do with that? Oh, sometimes, Abby, you'll need to use or find an angle. So if, I said you traveled 15 meters to the west, and then you traveled north 10 meters, and then I wanted to know what the resultant between those was, I could ask at what angle you were traveling, or in Physics 11, you'll be given the angle and asked to find things like the resultant. So yeah, I don't want to focus on the trigonometry type questions because you won't encounter them very often. And it's not something I think you need to learn in grade 10. I'm pretty confident it's a grade 11 topic. All right, so speed. This is the distance an object travels in a given amount of time. You guys are very familiar with speed. There's speed limits on roads. You're driving, we talk about speed all the time, how fast you're moving. Generally, we don't talk about things like running, how fast I was running, but we can. But if you maybe ride your bike, you have a speedometer, you drive a car, most of you are getting to that age, 16, where you're driving and you gotta watch out for those school zones and you gotta watch out for places where the speed limit drops and you need to slow down. So speed's really common. In physics, we introduced an idea called velocity, and we'll talk a lot about velocity. And velocity is speed with a direction. So it's kind of like distance, displacement, speed, and velocity are kind of related. Speed is just how fast you're going, and velocity is how fast you're going with a direction associated with it. So we call speed a scalar and velocity a vector. And to kind of demonstrate that, we have the picture of gondolas. So if you've ever been to like Big White or Silver Star, or maybe you've been up a gondola to some mountain peak, when we talk about speed, these gondolas are going at the same speed. One is, they're all attached to the same cable, so as the cable rotates, the gondolas all move at the same speed. But if I were to ask you about velocity, well, that's different. Now the gondola that's going up the hill has, let's say, a speed of 30 meters per second, but now it's going up. And then the one that's going down the hill might have a speed of 30 meters per second, but it's going down. So their speed is the same, but their velocity is different. They're going in different directions. So that's kind of the distinction we like to make there. There's a few other terms you'll run into. Instantaneous velocity is exactly what it sounds like. Instantaneous. If I want to know how fast you're going at one instant, that just means, how fast are you going right now? Or how fast were you going when you're in your car, when you passed the 7-Eleven this morning? So instantaneous velocity is a velocity at one point in time. Not over a large period of time, just at one point. And then we have something called average velocity. And average velocity is your velocity averaged out over a longer period of time. So instantaneous is at one point, average is over a long period of time. So there are some equations that we need to know. Not need to memorize, just need to know where they are. And you guessed it, they are in your data book. So this is the very last page of the data book. You'll recognize the common isotope pairs chart and then all this alpha, beta, gamma stuff that we talked about, the radioactive symbols. At the very bottom of the page, on the very back page of your data booklet, these are all your physics formulas. And there are also different units and the measures for each of those units. So distance is in meters, time is in seconds, minutes, hours, and years. So the symbols you'll encounter when dealing with those things. So meters is M, minutes is MIN. Don't get those confused. Speed, you think, speed should be S, but S is already taken by seconds, so we don't want to confuse speed and seconds. And then year is A, which is somewhat confusing, but it comes from, I'm going to assume it's Latin, that's annum. Year is one annum. Anyways, there you go. So here are all your physics equations. These are the ones we're going to use today. And then when we talk about acceleration in Unit 9, we'll use the additional ones here. So For now, we're going to talk about these three sets of equations. Do you need to memorize them? Of course not. They're here, but after you use them a bunch of times, you'll probably have it memorized anyways. It's just kind of one of these things that sinks into your brain as you see it a lot. So VAV, this all kind of looks quite confusing. So let's just maybe jump over to OneNote here. I was in OneNote, and we'll look at some of these questions. All right, see if we can't define some of the stuff that's happening here. I'm gonna just jumbo this up a little bit, a bit bigger. That's better. You guys can probably see that a lot better. So what is the average velocity of a dog that takes 4 seconds to run forward 14 meters? So the average velocity is how much distance you've traveled in a given interval of time, which sounds really confusing, but if you think about it, if I say I'm traveling 100 kilometers per hour, what distance am I traveling in what given amount of time? If you think about it, 100 kilometers per hour. I'm traveling 100 kilometers every hour. Or if I'm, in a city, 50 kilometers per hour is the speed limit. So that means at that speed, if you drove that speed for an hour, you would cover 50 kilometers per hour, or 30 kilometers per hour. That's what we're talking about here. How much distance are you going to travel in a given amount of time? Now, when we're talking about cars can go really fast. We can travel really long periods of time, and we can travel really far distances. But when we're talking about like humans walking and moving and running, well, I can't really run at 100 kilometers per hour. My body is just not capable of doing that. So instead of units of kilometers per hour, when we talk about people moving, we usually talk about how many meters they travel in a given amount of time, which we use seconds. So that's what's happening here. All right, so the equation on the back of the formula sheet is VAV, which is average velocity. So it's actually a little v. My v kind of looks like a capital one. AV, so the average velocity, VAV, is the change in position over a change in time. So that is this first equation here. Average velocity is change in position over a change in time. So what does that mean in terms of this formula? Well, it's kind of confusing because I have this triangle, which I don't really remember what those things mean, and I have this little subscript AV. What is this all talking about? So let's maybe just kind of define these things here first. The VAV is average velocity. And the triangle means change. Does anybody remember what we used the triangle for in math? What section that was? When we use the Greek letter delta, and this is a change, A-N-G, in time. Rise over run, perfect. We were talking about slope when we talked about the deltas. We said change in y coordinate over a change in x coordinate. So your change in your vertical over your change in horizontal. And today we're actually going to do the exact same thing with this formula. Instead of talking about a change in y, we're going to talk about a change in position. Change in x is a change in time. So it's the exact same idea. Kind of convenient that what you're learning in math you're using in science. Coincidence? I don't think so. But it's the exact same formula for slope. So we're going to actually talk about some graphs in a little bit. And we're going to actually use this exact formula to do the exact same thing we did with slopes in math, except instead of x's and y's, we're dealing with d's and t's. So same idea. So looking at the question again, we've kind of established what the formula means. What's the average velocity of a dog that takes 4 seconds to run forward 14 meters? Now, one thing that's kind of confusing in using this formula is that we don't really have a lot of information, but it's kind of assumed to be there. When it says a dog runs forward 14 meters, we know the dog is starting at 0 and then it's just going forward to 14. It doesn't say, hey, the dog started at 2 meters and then ran for 18 meters. How far did the dog run? It just says it ran for 14 meters. So implied in that 14 meters is that it started at 0 and it ended at 14. The same thing goes for time. The time is 4 seconds. It doesn't say the timer was going, the person started running at 10 seconds, and then we finished the race at 15 seconds. No, it just says it took 4 seconds. So the initial time you're dealing with is just 0. It doesn't say it, but it's implied in the question. So if you want to make your life a little bit easier, and I don't have a problem with you doing this, you can kind of deal with this question like this. Instead of doing this V average, just think about it as velocity is distance over time. Lose the subscript AV, lose the change, the triangle in front of the D, lose the change in front of the T, just velocity is distance over time. That's fine. You're going to end up at the same spot. So how far did the person go? Well, what do I know from the question? I know that this person took 4 seconds, so that means time is equal to 4.0 seconds. And I know that the person ran forward 14 meters. So the distance is 14 meters. So what am I going to do? Well, I'm going to plug in the distance is 14 here for the D. I'm going to plug in time was 4 seconds for the T. And then I'll continue on from there. So I have 14 meters divided by 4.0 seconds. 14 divided by 4, I don't know what that is. Actually, I do, it's 3.5. Plug it into my calculator anyways, just to make sure. So I end up with 3.5. Now, this is where physics, or physicists I should say, or physics teachers mainly, we get really angry. Because when you have an answer, you have to include units. And because we found a velocity, which is a vector, we need to include a direction. So what units and what direction are we going to associate with this 3.5? And how do you know? So you can throw it in chat. What units am I using? And what direction is this thing going? And then we can kind of take a step back and think, does that make sense? Can a dog move at that sort of rate? So meters per second, that's great, Taylor. And how did we end up with that? You too, Anna? One really cool thing about physics is our units, when we put them into an equation, they will always work out. So what do I mean by that? Well, if I put meters on the top of my equation, I put seconds on the bottom, I do the calculation, my answer is going to be in meters per second. It's just the way it works. Sometimes your units are going to cancel out, and there's whole parts of chemistry and physics just completely based on canceling your units out. So we've done a little bit of stuff in math based on unit cancellations, and that's what we're doing here. So meters per second, and then we included a direction. The only direction we were given in the question was forward. So I don't know what direction is forward. Could be up, down, could be north, south, east, west. It doesn't matter. If the question says forward, I'm just going to write forward. That's no very good F. So in physics, units and direction are extremely important. If an equation has meters per second in the question, would you change it in the answer? You would just have seconds in it. Generally speaking, Taylor, that's not gonna happen. If you have something like meters per second in your question, you're gonna end up with meters per second in your answer. So you're never going to change your units. Whatever is in the question is going to be in your answer. We'll look at some examples of that in a minute here when we start to do some unit conversions. All right, the next question. A boat travels 420 meters east in a time of 120 seconds. What is the boat's average velocity? The most important thing is to just identify what you have in your question. And at a very basic level, if you don't even kind of understand what's going on in the question, like a boat traveling 420 meters, 120 seconds, it's all kind of confusing. If at a very, very, very basic level, you can identify what you're given in the question, you can look at a formula that has those parts to it, you can solve and go from there. So that's what I'm going to kind of do, and it's a really great way to kind of think about physics type problems. I have this 420 meters east, and I need to think about what that is representing. So in this case, 420 meters east is going to be my distance, or the letter D. Then I have 120 seconds. That's how long it took. 120 seconds is going to give me a T for time. And I think it was Alex in math class said, "Hey, Mr. Borden, why do you draw your T's like that? Why, like when I write a normal word, I don't draw my T with like a little bottom to it." It gets back to the idea of physics equations. You can end up something like D is V naught T plus 1/2 AT squared. This is a grade 11 equation, but in this equation, you end up with a T and a plus sign next to one another. So every time I write T, I always put the little bottom on it. It's just good habit, so I don't end up with an equation that looks like D is V naught T plus 1/2 AT squared. Are they T's? Are they plus signs? I don't know. It can get confusing. So it's a good habit to get into, to distinguish your T's from your plus signs. Start with good habits now. All right. The question asks us to find the boat's average velocity. So this is VAV, and I don't know what it is. I'm going to try to find it. So again, at a basic level, you're trying to find average velocity, you're given distance and time. You can just jump to your formula sheet and say, okay, are there any equations here that have average velocity, distance, and time in them? Those are the three things I have: average velocity, distance, time. So if I look, I see that this first one has average velocity, distance, and time, and it's already solved for average velocity. Now, all of these equations have the same letters in them, D, V, and T. But we want to find one that has the average velocity, the thing we're trying to find, already isolated. So it's the same equation we just used, and perhaps I'm making this more difficult than it needs to be, but that's okay. V average is equal to change in position over a change in time. And again, if you just want to think about this as velocity is distance over time, I'm okay with that. Just simplifying it, getting rid of all the subscripts and triangles and things that just confuse students. So I'm trying to find this. I don't know what it is. The distance I traveled was 420 meters, and the time I traveled it in was 120 seconds. Another sort of physics type convention is when you're doing equations, you don't always want to put in the direction into your equation because it ends up making things really messy. So I'll include units in my calculations, but I won't include directions until I get to the very end, just because it's just so confusing and it doesn't really help anything along the way. If I know I'm traveling east, my answer is going to be east. So 420 divided by 120. It's going to be a decimal answer, so let's do that in my calculator. 420 divided by 120. 3.5. All right. So I end up with 3.5 meters per second, and this is where I will include my direction again. So I started in my question with a direction of east. My answer should be east as well. How do we feel about that? Are we doing okay? Does it kind of make sense? Getting warmed up? Getting your calculator on? You're good? Good. Yeah, perfect. Again, it starts off pretty basic. You got 3 variable type questions where you're given 2 pieces of information. You're asked to find the third. You've done way more complicated stuff in math. So that's the good news. All right. These next couple questions are the same types of questions, the exact same process, except they're not asking for the average velocity. They're now asking for, in this question here, what is the displacement? So you're looking for d. And what is the runner's displacement for the third and fourth example? So you're asked to find the displacement. What are you given? Well, in this case, I have a bicycle that travels 8 meters every second, and it's important to be able to recognize that meters per second for units represents a velocity, or an average velocity, and I have 15 seconds, which is going to give me a time. So I'll do number 3, you guys can do number 4. I have 3 things, distance, velocity, and time. I'm asked to find distance. So on my formula sheet, I'm going to look for an equation that has distance already isolated. And what I mean by that is this second equation has distance by itself already, which is nice because I don't have to go and isolate it. I don't have to rearrange the equation. It has d solved already. So that's the one I'm going to use. Change in d, or change in position, is the average velocity times the time. So change in position is the average velocity multiplied by time. Or if you just want to simplify this and lose all the nonsense, distance is velocity times time. Now, I know the velocity, it's given in the question, 8.0 meters per second, and I know the time. The time was also given in the question as 15 seconds. Now, I'm not going to include my direction in the question just because it gets kind of messy. So I'm just going to kind of plug away here. 8 times 15, what's that, 80, 120? 120. Now, think about our units. I'm multiplying meters per second times seconds, or I'm looking for an answer of a distance, how much displacement, I should say. What was the displacement? So I should have an answer in meters. And that's kind of the unit I was given in the question was meters. It turns out that I have, if you think about this meters per second as being a fraction, I have meters on the top, I have seconds on the bottom, seconds on the top. They cancel, and I'm left with units of meters. I don't want you to get too caught up in the unit cancellation type stuff yet. If you can just think about it, oh, I'm trying to find a distance, so my answer should be in meters, there you go. One other thing I need to include here is my direction. So in the question, the distance was north, so that means the velocity was north. So my distance should also be north as well. So I'm going to include that in my answer. So 120 meters north. There you go. I want you guys to do number 4. It's the exact same process. I have a feeling it's probably similar to something that's in the learning guide, or it might be the exact same question. A person at the starting line runs west 6.5 meters per second. What is the runner's displacement after 12 seconds? So it's almost the exact same question as the previous one. things are just mixed up a little bit, and instead of a boat, we have, or a bicycle, sorry, we have a runner. So take a minute and do that. I won't put a timer up, but just see if you can get that figured out. And when you're done, maybe throw your answer in chat, and we'll see if everybody agrees or disagrees. And it happens to me all the time when I teach my class at KSS. When I'm trying to put something in brackets, it automatically defaults to one of the little pictures, and I get really frustrated. So I've been there before. Don't sweat it. All right, so we have 91 meters, we have 78 meters, we have a 9 west, and we have 78 west. Yeah, it's just a default in Blackboard. I can turn it off, but it's kind of fun to see the little pictures every once in a while. All right, let's see what we can do here. What information am I given? So I see this 6.5 meters per second. I know that's a velocity. I'm trying to find the displacement, and then I have a time of 12 seconds. It's going to be the same formula, and I'm just going to keep it really simple. I'm going to write d as velocity multiplied by time. Not going to include the triangles and the v averages and all that nonsense. Typically, it just gets really confusing. So the velocity was 6.5 meters per second. And again, I'm not including direction just because it's going to make things more messy. And my writing is messy enough as it is. So 6.5 times 12, 78. And I'm looking for a distance. And in the question, the velocity of the person was west. So my answer should be 78 meters west. Oh, you did the one in the assignment. Yeah, if you haven't noticed, the questions in the assignment are almost identical to the ones in the notes. It's just they switch the numbers up a little bit. So there you go. So that was that. So well done, guys. 78 meters west. Make sure you're including units of meters and then your direction west. Both those things are super duper important. I'm going to jump back to my PowerPoint here. I'll go through a few more slides. I think there's a couple more examples, and then we'll take a bit of a break for a few minutes, and then we'll come back and this is actually it for Unit 8.2. We'll look at 8.3 as well. So we did that. Concept check, just thinking. I'm not going to do any calculations here. If you're driving in a car and you glance at the speedometer, what does this tell you? So what is the speedometer actually telling you? Is it talking about a distance, a time, a speed, a velocity, a displacement, a position? Which one of all of our fancy vocab terms is the speedometer telling you? It's kind of gives it away right in the name. And then the second one, at the end of a long trip, you know how far you've traveled, and you know how long it took. And this gives you the tools to solve for what. So concept check number 1, you're doing your written driver's test. You're trying to get your L. Yeah, so the speedometer tells you your speed. Exactly. Perfect. And of course, the word speed is right in there. Now, we don't want to confuse it with velocity because velocity has a direction associated with it. So your speedometer doesn't tell you which way you're going. It's just telling you how fast you're going, which we call your speed. How about the second question here? You know how far you traveled because your odometer told you, and you know how long it took because you checked your watch when you left, you checked your watch when you arrived. Given those two pieces of information, what could we solve for in terms of some of the variables we've been talking about? You know how far you've traveled, you know how long it took. So we have a distance and a time. What could we get from those distance and the times? It's an exciting time for grade 10 students. About mid-year, a bunch of people have gotten their L's and are working on their N's and all that exciting stuff. Taylor, we'll do a bunch more examples with the different things. So the first thing, Taylor, to try to figure out which one to use is, what is the question asking you to find? Is the question asking you to find a time? Is it asking you to find a velocity? Is it asking you to find a distance? And once you've established which one of the three things the question's asking you to find, then look for the equation that starts with that. And that's going to be the one you're going to use. So we'll look at a few more. Once we get into the acceleration portion, we'll use all of the equations, not just the first three. So for the second question here, we know how far we've traveled, we know how long it took, we can find our average velocity. Because we have our total distance traveled and we have our total time, so we can divide the distance by the time to get an average velocity. That doesn't tell us how fast we were going, 3 hours into our trip, or when we passed that giant chair on the side of the road. It just tells us, over the entire trip you traveled on average this fast. Of course, there might be construction, you might have to slow down for portions of your trip, you might get to go really fast, straight part of the road, higher speed limit. So average velocity is just the speed averaged out over the entire time interval. Yeah, we're going to do unit conversions right now. Converting units. Maybe we won't do unit conversions right now. The last section, 8.3, is super short. So let's finish up to unit conversions and then we'll take a little breather and then we'll go over some unit conversion stuff after a quick break. So how would you describe it to somebody if I said, hey, the car's velocity was negative 25 meters per second? What does that mean to say negative 25 meters per second? Of course, meters per second is a velocity, but what does the negative mean? How would we describe it? Is there a way to describe it, or is it just like, it's just negative? That's what it is, Mr. Borden. That's all there is to it. And then you might want to jump onto the second one here. Two escalators move up and down between floors. One's going up, one's going down. Compare the speeds and the velocities. Yeah, there's actually a couple things that can happen as a negative velocity, and Ava, that's really good. You got it. So we can talk about it as being a direction that we would assume to be negative. So we could say the car was going to the left or the west, or if we threw the car off a cliff, drove it off a cliff, it could be falling down at 25 meters per second. Perfect. Is there another way we could describe a negative velocity? So things like left, west, down, or south, those are all things we associate with negatives. There's one other way that is fairly common. talking about a velocity being negative. And you guys that are all learning how to drive do this every once in a while, probably when you first leave your house or maybe when parking. Yeah, perfect. So in comparison to another Abby, yeah, if we always talk about things that are going forward as being positive, as soon as I talk about something being negative, it could be going backwards. So that's good. If you put your car into reverse, you have a negative velocity. We normally associate things with forward as being positive, backwards will be negative. So those are all sort of great answers. So you guys, seems like you have a pretty good grasp of this. The escalator question, it's kind of like the gondola question, but just in a different type of thing. So now that we know a little bit more, the gondola or the escalators are going at the same speed, but their velocities are different. So the people going up have a upward velocity, where the people going down have a downward velocity. So the velocities are different, but the speeds are the same. So that's getting back to this vector scalar type thing. So velocity has a direction, speed does not. So converting units, I think we should take maybe a 10-minute break. I think 10 should be good. And then we'll talk about some unit conversions, and then we'll get into graphs. And that should be a good spot to end for the day. So yeah, let's take a 10-minute break, grab a drink, grab a snack, get up, move around. Don't just sit in front of your computer. And I'll see you guys back in 10 minutes, and we'll talk about unit conversions. Hi guys, welcome back. If you maybe just want to start with a green check mark just to make sure we're all getting through to you and you guys are all there, not just talking to myself. We'll do some unit conversions and then we will move on. So, thanks guys. Unit conversions, we've actually done some questions very, very similar to these in math. We did, we were converting from things like centimeters to inches or miles to, centimeters or kilometers. We did it with distances, imperial, metric, the two systems. So exact same principle. And one of the methods we used when doing those types of conversions was the unit conversion method that we're going to look at here today. So you've seen this stuff before, which is kind of, again, not exactly a coincidence, but here we go. You're going to see a lot of questions like this, so I'll show you the long way of doing it, and then there's a little bit of a trick that you can use, make your life easier, but you have to memorize it. So I'll do an example, and then I think you guys should be okay. 75 kilometers per hour, and instead of writing it like, normally I'd write meters per second like that, or kilometers per hour, I'm gonna write it on top of one another like a fraction, just to kind of make things a little bit more straightforward. All right, now up at the top here it says, 1 kilometer is 1,000 meters and 1 hour is 3,600 seconds. So these are things that you could, a kilometer is 1,000 meters is something you should know. An hour is 3,600 seconds. Might not be something you just know off the top of your head, but 1 hour is 60 minutes and 60 minutes has 60 seconds. So if I'm going from hours to seconds, I'm going to multiply 60 minutes in an hour times 60 seconds in a minute. 60 times 60 is 3,600. So there you go. Now, I'm going to do like a multiplication here. It's actually going to have 2 steps. And it's going to look kind of like this. So we're starting in this question with kilometers per hour, and we want to end up with an answer in meters per second. So this is the process that I'll recommend. If I have kilometers on the top, and I start with kilometers on the top, I want to get rid of it. Where is it going to go? And I want to end up with meters on the top, so where am I going to have to put that? So in terms of unit cancellation type questions, if I have kilometers on the top, I want to get rid of it, I'm going to have a fraction with kilometers on the bottom. So I'm going to put kilometers on the bottom. Now I want to end up with a unit of meters on the top. So what is the relationship between kilometers and meters? Well, I know that 1 kilometer is 1,000 meters. And that's just something I need to know. The second part of my unit cancellation is I have units of hours on the bottom, and I want to get rid of hours, so it's on the bottom, I'm going to put it on the top. And I want to end up with seconds on the bottom, so I'm going to put seconds on the bottom. And the relationship between hours and seconds is 1 hour is 3,600 seconds. So I'm going to go through this now, and I'm going to actually physically cancel my units. I have kilometers on the top. I want to get rid of it. I put it on the bottom. What else can I get rid of? Well, I had hours on the bottom. I want to get rid of it. I'm left with hours on the I put hours on the top. What am I left with? I don't have anything to cancel out meters on the top, and I don't have anything to cancel out seconds on the bottom. So those meters and the seconds are going to go and give me my units of meters per second in my answer. Now this is where the math comes in. I have 75, 1,000's on the top, 3,600's on the bottom. So in my calculator, I'm going to go with 75 times 1,000 divided by 3,600. So 2 steps, 75 times 1,000 equals, divided by 3,600 equals, or you could probably just plug it all in one go, and you end up with 20.8 meters per second. And that is how we do a unit conversion. Do it, there's always going to be 2 steps along the way, and it's the exact same process. The sort of opposite type question is you could be asked to convert meters per second into kilometers per hour, and I have a feeling that's what we're going to have to do next year. Another kilometers per hour to meters per second. All right, I'll set it up and then you guys see how you can do 95 kilometers per hour, and I'm going to multiply it. I have 1 fraction, 2 fractions equals, and I want to end up with an answer in meters per second. So I'll give you a minute to see if you can get your units in there and see how you do it and see what answer you get. So just throw your answer in chat once you're done. 95 kilometers per hour into meters per second. All right, we have a few 26.3s or 26.4, 26.4, 26.5. Perfect. I don't know if that's the right answer, but let's see if we can do it. Now I'm not gonna try to confuse you, but I'm gonna do it a little bit differently just to show you that you can do it this way. Now, if I wanna get rid of hours, I can put it on the top. I wanna end up with seconds on the bottom. 1 hour is 3,600 seconds. And then kilometers are on the top. I wanna get rid of them, so I put them on the bottom. And I want to end up with an answer of meters. 1,000 meters is 1 kilometer. Now, remember, because I'm multiplying here, the order of multiplication doesn't matter. So if I do my time first and then my distance second, I'm going to end up with the same answer. So there's no problem with doing it this way. So I'm going to take 95. I'm going to kind of look across the top here. 95 looks like I'm going to multiply by 1, multiply it by 1,000, and then I'm going to divide by 3,600 and then divide by 1. And of course, the actually dividing by 1 and multiplying by 1 you don't have to do because it's not going to change anything. But anyways, 95 times 1,000 divided by 3,600 is going to give me 26.38 or 26.4. Perfect. So you guys were well on your way there. Now, generally speaking, we won't see a lot of questions where it just asks you to convert from one thing to the next. Generally speaking, you'll have a question like example 3 here. So a truck's displacement is 45 kilometers after driving for 1.3 hours. What's the average speed or velocity, sorry, in kilometers per hour and meters per second. So it's kind of a two-step type question. It gives you some information. You're going to have to figure out, first of all, its average velocity. And then you are going to have to convert it to meters per second. Anna, what do you mean by draw the table? Like show the multiplication every time? Is that what you mean by that? Yeah. The reason I'm going to say yes is because we're going to also end up doing some questions where we convert meters per second to kilometers per hour. And if you don't write it down, you're going to kind of mix it up. And that's what makes things a little bit tricky. So in order to not make mistakes, yes, write it down. What is the velocity relative to this other velocity, or what is the velocity relative to your viewpoint? How would we do those questions? So what you're getting into here is it's kind of relative velocity type stuff, and I guess it kind of leads into Einstein's relativity. Might be where you're going with it. I'm not sure where you kind of encountered it, but it's kind of a different way of thinking about the world around us. So in Science 10, you won't encounter anything relative to one another, but if I, for instance, just to kind of explain my point a little bit, Ava, if I asked you right now, how fast am I moving, Ava? What would you say to me? Is there really questions in the learning guide? All right. How fast am I moving right now? I'm not moving, right? But then the Earth's spinning. So I'm standing on the Earth and the Earth's spinning. So I'm rotating at a few thousand kilometers per hour. If I talk about how fast I'm going on Earth, Earth's rotating, we know that. Earth's also revolving around the sun. So I'm actually traveling several thousand kilometers every few minutes. So if I ask my velocity relative to the sun, well, I'm going really fast, zipping around the sun. Our point in the Milky Way galaxy, our solar system's moving, so I could talk about our velocity with respect to the Milky Way galaxy. The Milky Way galaxy itself is moving close, the universe is expanding, things are moving. I'm moving right now, but we're relative to what? If you talk about my velocity relative to the room I'm in, I'm not moving, you're right. But if you talk about my velocity relative to a spaceship floating above Earth or a satellite looking down on Earth, well, now I am moving. And then, Earth's moving around the sun. So if I ask my velocity relative to the sun, I'm moving as well. My velocity relative to the rest of the galaxy, I'm moving. So there's some sort of interesting things that come out of that. Tell, but everyone's second is different than anyone else's, but it's also small, you can't tell. He knows much more about it than I do. Yeah, I mean, there's some big ideas that can kind of make your brain hurt a little bit, so we'll try not to get into it here. If you take Physics 11 next year, we spend a whole chapter talking about relativity, time dilation, so moving clocks run slow. It's been proven. It was Einstein's theory, but you can actually prove it with clocks now. So really cool stuff that comes out of that sort of thing. So we'll look at that. Taylor will find out, I'll look at your question on page 4. But for now, I want to do example number 3 and see how we end up getting along here. And Taylor, this might go back to your question, how do I know which formula to use? There's 3 there in the first column. How do I know? So if I look, it's asking me what's the truck's average velocity in kilometers per hour. So I'm trying to find the average velocity, and I don't know what it is. What am I given? Well, I know that the truck's displacement is 45 kilometers, so that's a displacement or a change in position. And I also know that I've been traveling for 1.3 hours, and that is giving me a time. Thanks, Ava. I'll have a look at them before we leave today. All right. Average velocity, distance, time. There we go. I'm trying to find the average velocity, so I'm going to go to my data booklet. I'm going to go to the back page, and I'm going to find a formula that is solved for average velocity, or VAV. And it turns out the first one has all the information I need, has velocity, distance, and time, and it's already isolated for average velocity, so I don't need to rearrange it or anything like that. So that's the one I'm going to use. The average velocity is a change in position over a change in time. Or, to try to simplify things, velocity is distance over time. Either one is acceptable. How far did I travel? Well, I traveled 45 kilometers, and I traveled it in 1.3 hours. Now, one thing that I kind of harped on you guys a bunch in the math sections that we did last semester was that your units are really important. You got to watch for them. And in physics is even more important. You end up with units of kilometers and hours, which is something that makes sense. But I could be given a distance in kilometers and a time in minutes, and then now I have a velocity of kilometers per minute, which isn't something we really have any reference for. We talk about kilometers per hour. We'll talk about meters per second, but kilometers per minute or kilometers per second, those aren't really common velocities. So just be careful with your units. 45 divided by 1.3 is 34.6. So I'm traveling at 34.6 kilometers per hour. And I know the direction I'm traveling is north. So that's the first part of the question. 34.6 kilometers per hour, north. The second part asks to convert this to meters per second. So let's do that. 34.6 kilometers per hour times. And I want to end up with meters per second. All right, kilometers is on the top. I want to get rid of it. I am going to put it on the bottom. I want to end up with meters on the top. 1 kilometer is 1,000 meters. There we go. I have hours on the bottom. I want to get rid of it. I'm going to put it on the top. I want to end up with seconds. 1 hour is 3,600 seconds. So 34.6 times 1,000 divided by 3,600 gives me 9.61. We'll just call it 9.6 meters per second. And this, of course, is north. Check my units. Kilometers on the top and bottom cancel. Hours on the top and bottom cancel. I'm left with meters and seconds. That makes me happy. Now, I said that I would show you how to do it the long way, and then there's a little bit of a trick to it. Now, if we look at the last few examples we did, so the one we just did here, converting 34.6 to meters per second, and then if I just scroll up a couple questions before, we were converting 95 into meters per second, and then same idea. So I'm going to ask a bit of a question. If I draw some big green brackets here, and I think about the math in the green brackets, it's always going to be the same. I'm always going to have 1,000 on the top times 1 and 1 times 3,600 on the bottom. So if I were to simplify all of the math inside the green bracket, what am I going to get in terms of a fraction? Well, I'm going to get 1 divided by 3.6. So if I'm going from kilometers per hour to meters per second, all I need to do is divide by 3.6. It's kind of a shortcut. Because instead of going 34.6 times 1,000 divided by 3,600, it's just going to be 34.6 times 1 and then divided by 3.6. So it's kind of a little bit of a shortcut. If you're going the other way, if you're going from meters per second to kilometers per hour, everything inside the brackets gets flipped. You just literally flip everything. So instead of dividing by 3.6, you're going to end up multiplying by 3.6. So that is a shortcut. I don't want you guys to make silly mistakes by doing the shortcut, but if you want to think about it that way and you want to use that in terms of your calculation, then you can. So kilometers per hour to meters per second, you're going to divide by 3.6. Meters per second to kilometers per hour, multiply by 3.6. Make your life easier. If you remember it, great. If you don't, that's okay too. I have one more example, but I might as well get to some of the questions you guys are asking, and then I'll do this example, and then we'll see where we end up. So there was a few questions. Taylor wants number 9 on page 4, and Ava, you found some relative velocity questions on page 5. So let's jump to number 9 on page 4. Convert 20 meters per second to kilometers per hour. Show all steps. This is a good question. It's kind of going backwards. I like it. So let's do it. 20 meters per second. It's going to be the same 2 steps, and I have kilometers per hour. So I have meters on the top. I want to get rid of meters. I put it on the bottom. I want to end up with kilometers on the top, so it goes on the top. I have seconds on the bottom to start. I want to get rid of it. I'll put seconds on the top. And I want to end up with hours. So I know that 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. And it seems really obvious, but sometimes students will mix up these sorts of things. They'll say 1 second is 3,600 hours, just because they're kind of getting to cruise control and aren't really thinking. So make sure your units kind of make sense. This is going to be 20 times 3.6, which is going to be 20 times 3 is 60. It's going to be 72. 72, I'm thinking. In fact, 72. So that was number 9. Maybe a good idea to go over some of those questions on page 5 just in case it pops up in an exam or something. For sure. So there was that. Hopefully that helps you out, Taylor. It's just the opposite process of the previous examples. Was the average velocity of the car that moved 40 kilometers east and 80 kilometers west in 2 hours? How far would if a car is 40 kilometers an hour in 10 opposite direction, what's the velocity of a car relative to b? Okay, so fair enough. These are kind of like the vector questions we did for moving, but now we're talking about velocities instead. So let's draw a picture. So car A, here's car A. And car A is traveling 40 kilometers per hour. So there's my vector for car A. Car B is at 10 kilometers per hour in the opposite direction. So there is 10 kilometers per hour in the opposite direction. What is the velocity of car A relative to car B? So if you were a person standing in car A or sitting in car A, how fast would you see the other car move past you? So if we kind of think about the velocities adding up, what's going on? What do we think? Car A is 40, car B is 10. What is the velocity of car A relative to car B? 30, 30, 30, yeah. So it would seem that, just trying to make sure I'm getting the right perspective here. So 30 kilometers per hour. You could write something like in the direction of car A. It's nice to have a direction. 30 or 50. Yeah, relative to one another, the difference in velocities can be 30. If they were both going the same direction, now you've got me all confused here. Ava, I'm happy with this. I'm thinking the question's kind of worded vaguely in terms of like where your reference is. So what is the velocity of car A relative to car B? It doesn't really say where we're looking from. Let's see if we can do 18 and see if it makes any more sense. So if you're walking at a constant velocity of 8 kilometers an hour, it's pretty fast for walking. So here you are going 8, and then a car passed by you at a speed of 30. So here's a car. And the car was going, let's make that bigger, 30 kilometers per hour. What was the car's velocity from your viewpoint? Now, I just see your point here. It says in the back it's 50, and I kind of can see why. That seems to be what's going on, but I'm still unhappy with 17 because it doesn't really say where you're kind of viewing these things from. Are you viewing it from the person in car A? Are you standing on the side of the road viewing it? At least in question 18, it says the car passed by you. What is the car's velocity from your viewpoint? At least that makes it clear that you're walking at 8 and then the car is traveling past you at 30. So if you're going at 8 and it's going past you at 30, then how fast does it look like it's going? Well, it looks like it's going 22. Think about it this way. If you were walking at 8 and a car was driving beside you at 8, how fast would it look like the car was going? If you were in, a big warehouse where the wall was blank, you couldn't see anything. If you're walking at 8 and you looked at the car and the car goes past you at 8, well, it's not passing you, it's just going to be right beside you the whole time, so it doesn't look like the car is moving from your viewpoint. So that makes sense. Now if the car is going 9, well, now it looks like the car is actually moving 1. So I guess it's kind of a little bit different. So what did we decide here? This is going to be 22 kilometers per hour. It would seem like it's passing you at. And then what does 19 look like? A car A is at 70, car B is 50 in the same direction. What's the velocity of car A relative to car B? The relative velocity is going to be, so there's my 50, there's my 70. So if you are in car A, looking at car B, it would look like it's going 20 kilometers per hour relative to car B. It doesn't really work out like the opposites. I guess when you described it by saying if they're going in the same direction, you subtract, and if they're going in opposite directions, you add, that would make sense. But the questions can be difficult because of asking from different perspectives. So you can get different answers if you're asked to look at car A from B or B from A, or if you're looking from the side of the road. So to come up with like a general set of rules for all questions, it's difficult because you're going to have different circumstances each time. So I don't want to say it's always going to be if they're going in the same direction, subtract, if they're going in opposite directions, add, because that won't be the case depending on where you're looking from. So hopefully that makes sense. Again, relative velocity is definitely a grade 11 concept. A lot of stuff from this is a grade 11 concept, so is there a strategy? You just want to know how to do it. Use your brain, I guess, is my suggestion to you. That's the best strategy. So depending on what the question's asking, you're not going to see a question like this on an exam. So it is good, you'll be ahead, but now I'm wasting time teaching you grade 11 stuff that you're going to have to learn anyways next year, so if you take physics 11. So it's not that good in the long run. So there you go. Those are those few questions. 11:15. I have one more question from the notes that I'll go through just because it's a bit of a trick question, and then we might call it a day there. I'm not going to jump into 8.3, I don't think. Although it's really straightforward and you guys will do fine on it. We don't need to rush through this stuff. What do you use physics for in real life? Oh, that's a dangerous question. Physics is a really broad area of science, so you can use physics. Everything from the computer screen you're looking at involves physics to the guy who delivered your screen. Physics talks about motion, physics talks about optics, so if your internet connection, how that gets transmitted from, TELUS office down on Enterprise to your house, probably goes through maybe a fiber optic cable, so the fiber optics is physics. How to transmit data packs, these are all sort of physics concepts. Sound is physics, so how the speakers are vibrating with the electricity that's moving the electromagnet in the back of it. Physics really spends a lot of time talking about how sort of everyday things around us work and how to make them work. The lights in your house, electricity, all physics. Still confused about number 9 on page 4, Taylor? Let's go back. So if you do it the way you showed us first, you multiply and divide by 1. So wouldn't it just be what you started with? So in this case, Taylor, we're going to take 20 and then multiply it by 1, multiply it by 3600. So in my calculator, it's going to be 20 times 1 times 3600. And then I'll do the divisions. I'm going to divide by 1,000 and then divide by 1. And then I'll go with an equal sign there. So you definitely shouldn't end up with what you started with. You're going 20 times 3600 divided by 1,000, or 20 times 3.6. So that is what's going on there. Hopefully that clarifies that a bit. If you took physics 11, you can apply for a bunch of sciences in university, I think. Oh, you canceled out 3600. Well, that's not a good idea, Taylor. At least you found your mistake. What types of jobs primarily focus on physics? It's kind of an interesting question because there's a whole branch of kind of applied physics, and we call it engineering. So if you were an engineer, talk about You could be a mechanical engineer, you could build things, you could be a structural engineer, you could build bridges and roads. Electrical engineers talk about how much electricity can flow through different gauges of wire and stuff like that. So if you want to think of applied physics, then you're talking about engineering. If you want to think of pure physics, you could be an astronomer. So you can take astronomy type courses. There's down in, just outside of Karameas, there's the Dominion Radio Observatory. And there's a bunch of scientists there, physicists, who look at radio waves from galaxies and stars and try to, learn about the universe based on radio waves and all sorts of other things. What other pure physics types things are there? If you think of if you've ever heard of CSA, so Canadian Standards Association, they tell you if you're wearing steel-toed boots, they're CSA approved, or if you have a hard hat, it's CSA approved. So people who work for the CSA, they would take like a hard hat and they would drop a weight on it to see if the hard hat cracks. So that's kind of a pure physics job. Trying to think of other sort of directly pure physics. There's lots to do with optics. So you could, optics. I don't want to say you could be an optometrist because that's not pure physics anymore. It's kind of applied. But how do you use optics in your real life? Can look at things like the transparency of glass, how light gets reflected off glass a little bit. You could talk about what types of materials the glass should be made of to transmit large amounts of light. So there's really it's kind of hard to pinpoint exact jobs. If I think about pure physics jobs in Kelowna, there's probably not a lot. There's lots of applied physics, sorts of engineering type jobs in Kelowna, but pure physics, you might have to go to a big center for those types of jobs. Does med school need physics, or should you focus on chem and bio? Depends on what you want to do, but if you were going to go to med school, you would definitely want to focus on biology and chemistry. And you could be even more specific. You could do biochem, which is a specific branch of biology, where you would be able to talk about the chemistry within the human body, which would help you for med school type stuff. So there you go. I kind of got lost. You guys got me off track. That's okay. Last example, then we will call her a day because I won't be able to get the last section done. What's the displacement of an airplane flying 480 kilometers per hour east in a 5-minute time interval? All right, there's at least not two tricky parts in this question, but there's one trick to the question. And there's another sort of thing that's perhaps a bit different than the questions we did in class. So the question's asking, what is the displacement? So you're trying to find the displacement, or D. That's what you're looking to find. So I need to focus on finding an equation that starts with D. That's the first sort of thing. What other information am I given? So I have 480 kilometers per hour. That is definitely a velocity. It's telling me how many kilometers I'm traveling every hour. And I also have a 5-minute time interval. So I need a formula with distance, velocity, and time, but it has to be isolated for distance. So if I go to my data book, I see that in the first column here, the second one has distance already isolated, and it has the 3 variables I need: distance, velocity, and time. All right, so I have change in position, or displacement, is my average velocity times my change in time, and that all looks quite complicated, so let's just get rid of all the nonsense. D is V times T. Can anyone see the problem I'm going to run into here? Before I run into it, kind of help me before I make a mistake or before you make a mistake. It has to do with units. What's the problem with my units? Do my units match? Well, it doesn't really make sense to talk about units matching between things like velocity, kilometers per hour, and a time. But what is my velocity measuring my sort of speed in? Perfect, Anna. We have a velocity in kilometers per hour. And we have a time in minutes. Those don't match up. I need a time in hours or I need a velocity in kilometers per minute. So which one should we change? It doesn't matter. I mean, you could change whatever one you want, but I'd likely will change my minutes into seconds. So I'm just going to write a little note here. Units must match. And on an exam, either in the class or even your provincial, do you think that they will have the answer if you multiply 480 by 5? This is kind of one of these things where you're doing your exam, you're trying to get it all done in 3 hours, you take 480, multiply it by 5, the answer's there, yes, got it right, move on. And then you never really know, but you end up getting the answer wrong because your units weren't the same. So it's a common thing. So I'm going to convert time to hours, or I could convert everything to meters per second and seconds. It doesn't really matter which way you do it, but let's do this 5 minutes. And I want to end up with units of hours. So using all of the unit cancellation things we just did, going from kilometers per hour to meters per second, or meters per second to kilometers per hour, what are we going to do here? I have minutes on the top. I want to get rid of it. I'm going to put it on the bottom. I want to end up with units of hours, so I put it on the top. Now, we haven't talked about the relationship between minutes and hours, but you know what it is. You know how many hours are, how many minutes are in an hour. So if I have 1 hour, that is 60 minutes. So I'm not using 3600 here. I'm not going from hours to seconds. I'm going from minutes to hours, which is kind of a little bit different than what we've done so far. So don't get into the habit of going, okay, I'm converting times, I'm going to divide by 3600 or multiply. That's not what's going on. You have to use your mind a little bit here. So 5 divided by 60, or 5 times 1 divided by 60, is 0.83. Let's get black. 0.83. 0.083 is what I meant to say. There we go. So now I have my time in hours, and now I can do my question. So distance, how far am I traveling if I'm going 480 kilometers per hour, and I'm doing that for 0.083 hours. So do the multiplication, 480 times 0.083. I end up with 40. And my units are kilometers. My hours cancel top and bottom. And I'm left with kilometers, which makes sense. If your units don't work out, then you have a problem. And I'm traveling east. So I put in my little east here. Just for fun, let's say I did this incorrectly. I went distance was 480 kilometers per hour. And then I multiplied that by 5 minutes. So 480 times 5, not really interested in what that is, but notice what happens to my units. I would have something kilometer minutes divided by hours, which is a really, really strange unit. Nothing we'll ever talk about will be in kilometer minutes divided by hours. So you don't want to do that. Make sure your units match up and you end up with where you want to go. 20 minutes or so left, and it's not going to be enough time for section 8.3. Maybe I'll just look at the learning guide here and we'll see where we're at. So you guys should be good up to the relative velocity. So yeah, we should be good up to page 5. We haven't done graphing motion yet, and graphing motion will be 8.3. You guys can do all the graphing motion stuff. You shouldn't have any problems with it because we've covered it all in math already, but there's some kind of things that won't make sense probably until we talk about it. So if you want to continue on ahead, that's fine. You should do absolutely fine with the graphing motion stuff. But that's kind of where we're at in terms of these questions. So you should be good up to page 5, the end of page 5. The beginning of next class, we won't meet next week. I won't see you guys again for a whole nother week. It's a long, long, long break. Next week, you guys will have social studies and then you're doing the walking tour of downtown. And yeah. Does anybody have, I know Mrs. Wood had sent out some course information for you guys, and most of you who are continuing on in our grade 11 program picked your courses. If you're going to one of the schools in the wherever you're living next year, you've probably done a course selection thing with that school. But does anybody have any questions regarding the courses, physics, biochem, earth science, in general? I know you've probably talked about it a little bit in planning, but I mean, we've talked about it a bit today and we have some time. I only got a survey about what courses. Yeah, that's probably all you would have received. And then you kind of filled out the little, well, there was a questionnaire. She might not have sent it out yet. There might still be to come. So yeah, if you had any questions about that stuff, or jobs, or university prerequisites, or anything like that. Have I chosen the sciences I'm going to teach? No. We are kind of waiting to see which sciences people choose in order to pick one that is going to kind of service the most amount of students, because just the way the timetables work and how funding works out, I can't teach a course with like 2 students in it. I would love to teach a course with 2 students in it, but it's just not financially viable. So we're kind of a little bit have our hands tied a bit with what courses we can do. I'll be doing one for sure out of the big 3, so chem, physics, or bi. Probably chem or physics. I don't know that for sure. If you wanted to take 3, you'd likely do a couple through Central, sort of more correspondence style than what we've been doing. Is the survey determining what courses you offer? A bit of both, Ava. If everybody decides they want Physics 11, then I'll teach Physics 11. If only one person wants Physics 11, then we're not gonna teach it. You'll have to take a correspondence. So I don't want to, get myself too deep in the mud here by saying, hey, if everyone says we want this, we'll do it. That's just not a reality. There's a lot of moving parts here. So it's not just a matter of people saying what they want and then we offer it. You need to decide what you want based on working backwards. So if you plan on attending university, you need to say, okay, first year university, I want to be a botanist or whatever you want to end up being. So sort of think of a career path. And you don't have to pick a specific career, but you should identify an area where you want to go and then kind of work backwards. Okay, I want to work as an engineer. I'm really interested in electricity, electrical engineering. work my way backwards. Okay, I need to take physics, I need to take chemistry to get into that program, so I'll need to take physics and chem in grade 11, physics and chem in grade 12. So there you go. Yeah, and you end up with, biology is not easy. It's a lot of concepts, a lot of memorization, not as much process-oriented as like physics or chem, for sure. So that's kind of one of the considerations we're making with the courses we offer. Biology would be a really great course to take through correspondence because it's a lot of you reading. There's not a lot of process stuff, so it's like, we're talking about sea sponge. How does a sea sponge work? Well, it has all these cells, and the cells go together to form an organism, and it's in this phylum, in this kingdom, and things like that. So that's kind of something that you could definitely do through correspondence, a lot easier than something like physics or chem. So that's kind of where we're at. Do you guys offer chem bio as like one course? That's no, you have to do chemistry and biology separately, 2 separate courses. Yeah, and remember, you don't have to take 3 sciences, or you don't even have to take 2 sciences. You need a science in grade 11 to graduate. If you're going on to maybe do an arts degree, maybe you're interested in English or things like that, maybe you don't want to go to university, you just want to go to trade school, or maybe you just want to get a job and start working. You don't need to take 3 sciences for that. I have a physics degree. I went to university and got a science degree, and I only took 2 sciences in high school. I took chemistry and physics in grade 11 and 12, so I didn't take biology until I made it to university. And 2 sciences was enough to get into university when I went. That's all I took. And then I took a bunch of biology when I was in university. So there you go. If you're going to take physics 11 and 12, calculus doesn't really need to be a part of your course selections, but calculus is really great if you plan on doing physics or chemistry in university or pursuing any sorts of math. So basically, calculus in grade 12 is an elective. It doesn't really count as a math credit. It doesn't count as a science credit. And it's just a bunch of stuff you're going to learn in university. So it's basically like a first-year university. The first half of first-year university math is calculus. So you learn a semester's worth of university just to kind of get you ahead. So calculus and pre-calculus are different. Ideally, you'd take pre-calc 12 first semester, and then you could take calculus second semester. But there are, I don't want to overstep here, but I don't think there's any courses in university that will require you to take calculus to get into them. A lot of courses would suggest you take calculus. It'd make your life easier, but you don't have to take it. I took calculus when I was in high school, and it didn't really, it was good to know it, and I took calculus when I went to university, but there was lots of students in my class who didn't take calculus in high school and still did fine in university. So we'll definitely be semestered again next year, Taylor, for sure, semestered. It's just to line up with the timetables of schools and things and scheduling. So that's that. It doesn't seem like there's any other questions. We won't see each other again until, I might come climbing on Friday if you guys are interested in that. Lots of fun. Walking tour next week. I don't know what I'm doing. I might partake if I'm not teaching. That'll be fun. And then I won't see you guys again until the following week. So I think it's June already, or maybe the end of May or something. Crazy. Time flies. So basically we have 8.3, and then we have 2 sections in chapter 9. 2 sections? There's basically 3 or 4 lessons left, and we're done. So we're going to finish with about a week's worth of review time left, and we'll start to organize that. You guys can come in if you have questions. I'll get some practice exams out to you guys so you can start doing that the next time we meet. Seems really early, but that gives you a month to start reviewing. So we'll start looking at some practice exams next time we're together. The provincials, I don't know the date. It's on the end of June. I think it's the 24th or something. Yeah, thank you, Anna. Is there assignment for Unit 8 and 9? We'll probably do one assignment for Unit 9. On June 8th, we're going to go to KSS. And if you come to KSS on June 8th, we're going to do a lab. And that will count for your assignment for Unit 8 and 9. If you don't come, then I'll give you one to do online. So it gives everyone a chance to kind of do it. You want the model exams because it forced me to study one. Yeah. Abby, you had some questions about chemistry. So that's all I have to say for physics and course selections and all that. So if you want to take off, we'll see you later. Abby, you had some questions I'd be happy to go through now if you want to fire them in, or I can go to a learning guide or whatever you want. And we can go through that. We have a bit of time now. So if not, have a great afternoon, guys. We'll see you in a couple weeks. So long. And then we'll start reviewing and finish up this physics stuff. But for now, chemistry review. And most of you will be stumbling into the Module 2 exam eventually, so might benefit from looking at some questions. And if you don't want to type them out, if it's something I can just go look at online too, Abby, you can just say, hey, go look at this, or see where you're at. The learning guide's all loaded up, ready to go. Should you memorize compounds for things like glucose and table salt? Yes. Those are kind of really common ones. Things like, you should know what acetic acid is, which sounds really weird. There are some acids in your learning guide. So acetic acid, here nitric acid, sulfuric acid, hydrochloric acid. You should, I've just highlighted behind my head. There we go. You should know where all of those things are in your learning guide. You should know the basic hydrocarbons. So you should know what methane is. CH4. You should know what table salt is, or just NaCl. Glucose. I want to say yes to glucose because it turns up in the biology unit and it turns up in the chemistry quite often. C6H12O6, I believe. Hopefully I got that right. So there's glucose, you should know that one. Diatomic elements. Well, at least you did it there, Ava, instead of somewhere else, like a provincial or somewhere where it's important. Yes, and acetic acid is in the data booklet, so CH3OH. I think it's written differently in your data book, but it is there. So these are kind of really common things. Just like when we say water, you know what water is. You know it's H2O. It's just really common, so you've memorized it. Well, to scientists, things like methane, it's really common. CH4, you should know what it is. Table salt, NaCl. These are kind of just really common things to scientists. Should you memorize the strong acids? Strong bases have elements from the first two columns in the periodic table and usually do two. Strong acids and then other acids you could safely assume to be weak. I don't know, Ava. I want to say no. Don't worry about strong acids or strong bases. It's a chemistry 11 and chemistry 12 concept. I want to say chemistry 12. As long as you know the common acids out of the data booklet in Unit 4, so hydrochloric, sulfuric, nitric, acetic, you should be okay in terms of Science 10. So you get those, that's good. Do I need to know how to name things like cyanide, that doesn't have an ite or ate. I'm not sure what you mean by that, Abby. When we're talking about cyanide, it's one of the things that's on our common ion sheet. So there are a few things on the common ion sheet that end in ides, but you can just look them up, like hydroxide, cyanide. I think those are the only two. So I guess when you're doing your kind of naming, we talk about like sodium chloride, and we see a chloride, and we think, okay, chloride is chlorine. I look up Cl, it's there. But cyanide isn't on the periodic table. It's not an element. It's carbon and nitrogen bonded together covalently. So naming rules for polyatomics. Well, in general, right, for polyatomics, we're not going to change the ending of the name. So if it is NaClO3, that is sodium chlorate. It could be NaClO2, that's sodium chlorite. We could have NaCN, sodium cyanide. So we never change the endings of our polyatomics. We only change the endings of nonmetals, and they always get changed to ide. With acids, it's different. You get your eights go to ic, and your ites go to us. Those are the acid naming rules. So there's three types of acids. You have an acid in polyatomic, it's either going to be an ic or an us. You have an acid with just a non-metal, it's going to be hydrochloric acid, hydrofluoric acid. The ides. Hydrocyanide, hydrocyanic, hydrocyanous. I don't know that that'll happen. There's only two of them. You can't put H and OH together because that's just going to give you water. So that wouldn't happen. I don't know what HCN is called. That would be the only exception to the rule, HCN. I'm sure you could Google it. I don't know what it would be called, to be honest. It's not something that's ever really come up before, but it is an excellent question. HCN. Let's just Google it right now, see what it's called. Hydrocyanide, hydrogen cyanide. Here you go. It has a common name. Prussic acid. So it is definitely an exception to the rule. I've never really encountered it before, so hopefully you don't ever encounter it either. It doesn't even look like it has fromic acid, hydrocyanic acid. So it gets the hydro, and this is a common name, and this is a common name. So hydrocyanic acid. So it looks like it gets named like just HCl would or HF, things like that. Weird questions, but good questions. So those would be the only two scenarios. You'd have water, or you'd have hydrocyanic acid. Anything else? Any other fun chemistry questions? Feverishly typing. Look what I started. You guys are writing paragraphs. Lately, we've been watching a lot of wildlife documentaries. Eva, I love your comments. So sciencey. And they talk about what ocean currents do to the land. Are you talking about like El Nino, La Nina sort of currents, or talking about like the deep ocean currents where? Yeah, like in terms of climate change and ocean currents, and there's lots of really cool stuff about frequency of El Ninos and La Ninas and how they used to. Okay, Abby. As the ocean used to be fairly consistent in terms of temperature, and then we had a few El Nino, which was warming, and then it'd be normal, warmer, colder. But now it's every year is an El Nino or a La Nina. So it's really does a lot of interesting things, scary things to the atmosphere, which is another section that's in Science 10, but they took it off the provincial, so we don't often get to it because there's not often enough time. All right, I think you're good, Abby. Ava, you're going to keep getting smarter watching all these documentaries, which is great. Everyone else, I think we'll probably leave it there for today. See you guys in a couple weeks, and obviously get as much done as you can. You have a little break from me. So I hope you guys get outside and enjoy some of that nice weather. Today doesn't look like it's going to be that great for the weekend. Yeah, specifically some of the temperate rainforests that we talked about in class, unique because of their proximity to ocean currents and jet streams, which ocean currents drive jet streams in the atmosphere. Lots of connections here, Ava. I like it. Yeah, and think about us, right? That's why we're so dry in places like even like into the prairies in Calgary and things like that. Rain shadow that the Calgary area receives. They get some Chinooks in the winter, really warm temperatures and things like that. Pretty cool stuff. So there you go. Have a great one, guys. We'll see you when we see you. Thanks, bye.